The soap bubble in this problem has a thickness T that we're asked to find. Its index of refraction is 1.33, the same as for water, and it's floating in air. White light is incident on the bubble, and we're told two wavelengths, one that interferes constructively and one that interferes destructively. Before we can write the interference conditions, we need to count the number of phase shifts. On the first surface, the air-bubble interface, there's a phase shift because the index of refraction for the bubble is larger than for the air. But on the second surface, when the wave is reflecting off the bubble-air interface on the back, there's no phase shift because the index of air is less than the index of the bubble. So with one phase shift, the condition for constructive interference is twice the thickness equals m plus 1/2 times the wavelength in the medium, where m is an integer from 0 on up. And the condition for destructive interference is twice the thickness equals m lambda in the medium. We can replace these lambdas in the medium, lambda n, with the vacuum wavelength, lambda naught, divided by the index of refraction n. And rewrite both of these expressions using subscripts c and d for constructive and destructive. The left-hand sides of these two equations are equal, so the right-hand sides have to be equal also. Because the constructive wavelength, lambda c, is larger than the destructive wavelength, lambda d, we can see that m sub c, the order for constructive interference, must be less than m sub d, the order for destructive interference. And because there are no minima in between them, they must be different by 1. Now let's subtract these two equations so that we can solve for the order, either m sub d or m sub c. On the left-hand side we get 0, and the right-hand side gives this expression. We can eliminate m sub c, the constructive order, from this using our expression above, mc equals md minus 1. When you substitute that and rewrite this expression, you find this. Now we can solve this for the destructive order, m sub d. It equals 1/2 the constructive wavelength divided by the difference in wavelengths, constructive minus destructive. After substituting the values and calculating, we find that the destructive order is 2. Knowing that, we can come back up to our condition for destructive interference, solve it for the bubble's thickness T, and substitute all the known values, which shows us that the bubble's thickness is 338 nanometers.